Hello, I'm Krishna. For the pattern recognition project, I chose the following topic. I chose to model the COVID-19 cases using LSTMs. So, we know COVID has been a pandemic and affected us either directly or indirectly. So as a part of the project, I kind of used LSTMs or different types of LSTMs, so the LSTMs, bi-directional LSTMs, and convolution LSTMs to predict the next new cases of the COVID data, and I've trained the model using the USA and India data, and then and the results are compared using the normalized RMSE values. All right, let me take you to the code. Let me just run it, and by the time we finish the presentation, we'll get the results. And by the way, they're already included in the slides. So let's go to the overview of LSTMs. LSTMs, before talking about LSTMs, we should have to talk why LSTMs, because in order to model COVID data, which is highly nonlinear, non-stationary, and uncertain, the typical mathematical and statistical models would really fail or perform poorer. So using neural network techniques such as LSTMs and recurrent neural networks, which are best suited for sequence-to-sequence predictions, I thought would be better. And I'm not using recurrent neural networks because that could lead to vanishing gradient problems, which will not be the case with LSTMs. So LSTMs has 3 gates of same shape. It has input gate, forgetting gate, and output gate. So the basic thing what happens here is it will have 3 gates. The values of 3 gates will be updated for every time step, and once they get updated, we get the values of the next states, and the model goes on. So every gate takes the hidden state and the present input as their inputs, and then they process them with the sigmoid activation function. So the emphasis of the input gate is it will check whether the memory cell is being updated or not. The forget gate will control if the memory state is set to 0, and the output gate will tell you if the current state cell is visible. So if you can see here, this FT, this IT, and this OT. So once we get all the 3 values for one time step, we will be getting the values of the CT and the HT. But in order to get the CT and the HT, we apply the tan H activation function, and this tan H activation function really helps in not leading to a vanishing gradient problem, because it really provides a good distribution of gradients over a long period of time. And we use sigmoid activation function at the recurrent stages because they constitute smooth curves going between 0 and 1, and then in order to make the model differentiable. So and next, instead of and apart from using the LSTMs, I used bidirectional LSTMs and convolution LSTMs. So bidirectional LSTMs process the given information into 2 directions. That is, one hidden state processing the information from the present state to the next state, and the other hidden layer handling the information from the future state to the present state. And the outputs across both the layers are given to the same output layer. So basically, it is the bidirectional LSTM can be thought of as 2 RNNs, which are the 2 independent RNNs which are kept side by side. So these bidirectional LSTMs would really help in understanding the dynamic nature of the variability of the data, because it will have access to the feature values as well, and it could really model it better. And the other model I've considered is convolution LSTMs, or conv LSTM. It is nothing but the normal LSTM, but with the transformations of the input during the recurrent stage are made convolution in nature. So in these LSTMs, for example, if the input is a sequence of images, then the first image is passed on to the convolution layers, and then the result is flattened to a one-dimensional array. So in this case, the input is a time series data, so we can see we can see because it is convoluted, we could see how similar one input sequence of the input data is to the other, and we could learn the correlation between the different inputs. So it would be interesting as well. So the data set that I've considered is of India and the USA data, because these two countries are the top two countries with the most COVID cases. So I've divided the train and test in such a way that the training or the testing would have one part of the COVID wave, and the other part of the COVID wave is given as testing. Whereas in India, the half of the I've taken the data from 17th August 2020 to 18 May 2021 as training data, and the training data and the test data are same for both India and USA. For India, the training data covers up to the peak of the second wave, and then when the cases started to fall down, and this data is given as testing data. And similarly for USA, from the summer, after the summer 2021, the cases started to increase. So all the data before the summer is given as training, and data when the cases will started to rise is given for testing. And this is done deliberately because I just want to see how LSTMs would learn when the input, how they will learn if the input is changing abruptly. All right. So next is the data pre-processing and model architecture. So I used a min-max scaler to normalize the input data, and I convert, because it's a time series problem, I converted the data into a sequence embedding vector of 5. That means you give the first 5 time steps into an embedding vector as an input to the model, and it will predict the 6th value. And this implementation is a one-step ahead implementation. That is, if you give the data for 5 days, it would give you the day. It would give you the predicted value for the 6th day. And this is the model architecture for the different methods used. This LSTM, bidirectional, and the convolution LSTM. I've used a dropout of 0.2 after hitting layer 1 and a 0.4 after layer 2. And then the kernel size for convolution LSTM is 1. And let's go to the hyperparameter tuning. So first, before deciding on the hyperparameters, before deciding on go ahead and running the model, I actually tried to tune the hyperparameters, and the ones that I've considered are the running, the learning rate, model architecture, and the recurrent activation function. The optimizer that I've used is ADAM, and I've trained all the models for 200 epochs. And the procedure that I followed is learning rates are varied for different values of the 3 LSTMs for a 2-layer neural network and the 3-layer neural network. So in the 3-layer neural network, I added the 3rd layer of 32 units, and that's it. And then also I changed the recurrent activation function from sigmoid to ReLU. And then I checked which one performed better. So under all these combinations, I've taken 5 to 6 values, four values of learning rates, and then the 2 different architectures of LSTMs, and then I've taken 2 recurrent activation functions, and I've just tried to see which one fits better. And it says that for the learning rate 0.001. The best performance was observed, and that was a 2-layer neural network with the ReLU activation function at the recurrent stage. So if you can see, the RMSEs are calculated for all the models across all the learning rates. So this is the least, which is observed for bidirectional LSTM. So bidirectional LSTM actually performed better, and that's the reason I tried to show you the learning curves of bidirectional LSTM. So as the learning rate is really less, it is not learning that much, but when it hits the right amount of learning rate, it decreases and it stays and it settles down very fast because it converges fast, because it is the correct amount of learning rate, and it learns the data pretty fast. And for the other learning rates, if you could see, they either start at high error rates, or they don't stabilize at the output, and then they kind of have some spikes in the middle. So the results, so the finally obtained hyperparameters are stated here. The learning rate, this is the learning rate, and the 2-layer neural network is ReLU as a recurrent activation function. So the results are these. So the bidirectional LSTM performed better than the other 2 models. This is for the prediction for the training. As you can see, the blue one is the true, and the one which is really close to it is bidirectional LSTM. And also this is for India, and this is for the US. And US also, you can see the same thing. The blue one is the true, and the green is the bidirectional, which are really close. And then the test data, also, it actually, the bidirection performs really well, and these are the results. And the green is really close to the blue, which is the bidirectional LSTM. And then the main thing is that the bidirectional LSTM is able to get the trends right. See, when the, especially in the USA, when the data is increasing exponentially, the bidirectional LSTM actually is catching up to it. So, which is what I really wanted to see in the project, is that how well the model is catching up with the data, especially when the data is changing at a very high pace or abruptly. So these are the learning curves of the model. This is the validation set across the two data sets. These are the USA. If you can see, the bidirection settles up really fast for both models. And if you could see, so these are the results which are obtained. Okay, let me just go back and say, because in the bidirectional LSTMs, they have the ability to access the future values of input, and then also, I mean, and also they can go back and front. So this kind of model actually performs better, because it will have the access to both present, and it will have the future, and also it go to the past and come back to the present. So this kind of flexibility, sorry, I was searching for the word. This flexibility in the model really helps, and also and that's the reason the bidirectional LSTM performs really well. And if you see the convolutional LSTM, it's almost close. So after bidirectional, it is convolution all the time. So it is close, but because the data is a time series data, and which is and maybe not that, because convolution is maybe applied to more of images than the time series data. But then I found few papers who also applied convolutional LSTMs for the time series COVID prediction data, which I include in the report. And they also have got that, the convolutional LSTM is not performing well. So so these are the normalized RMSE tabulation results for both the models, for all the models across two data sets. If you can see, the bidirection performs better. It is the least for the training data and the test data across all the models for India. Not only for India, but also for the USA. So you could see that the testing data, so this is for India. If you could see the testing data, the root mean square value, the normalized is 0.05, which is quite less. And for the training is 0.02. And for USA is 0.06 for training and 0.12 for the testing. So okay, let me get back to the results. So yeah, these are the results. You could see that you could see all these results here. These are all run results here. All right, so thank you so much.